So something else that we see is you don't have to use left and right endpoints. You can use any point in each of those subintervals, and as n goes to infinity, that some of those areas still goes to the actual area underneath the curve. If we look at each of our intervals, for whatever n we're given, we can just pick any sample point from each of these intervals, and so we can denote it. Like from the first interval, I can pick any point between a and a plus delta x and call it x sub 1, and any point between a plus delta x and a plus 2 delta x and call it x sub 2, etc. So that's what's happening in this expression. So the area is the limit of this sum, where I'm evaluating my function at a sample point in each of these intervals that I'm calling x sub k, and then just multiplying. That's the height, this is the width of each rectangle, and then I'm adding them up, and taking the limit gives me the area. So here's an example with another function, x minus 2 ln of x. Now my interval is 1 to 5, and I'm going to use 4 approximating rectangles to find the area, an estimate of the area. So I'm going to take the length of my interval, divide it by 4, so my delta x is 1. So my subintervals, I've got 4 subintervals, each of length 1. And since we're using a right-hand estimate, each of my rectangles is going to have a height of that function evaluated at the right endpoint of each of these subintervals. So my height's going to be f of 2, f of 3, f of 4, and f of 5, respectively. And then I'm going to just find, since the width is 1 for each of these rectangles, all I really need to do is add up those function values, and I get approximately 4.425. That's, you can see that an overestimate, we can see that we have more left over here. But this rectangle, it's actually an underestimate for. But these other 3, it's an overestimate for. Here, we're being asked to find this, but instead use the midpoints, not the right endpoint of an interval, but use the midpoints of the intervals. So again, we're using 4 rectangles. We chop up our interval into 4 of delta x equals 1. Our intervals are the same, but our sample points that we're going to use to find the height of the rectangles is now different. So the midpoint of each of these subintervals is, here there's 1.5, the midpoint here is 2.5, etc. So these are going to be our heights. So summing those 4 heights up, I get approximately 3.84281. Since, notice that we might get a better estimate with the midpoint, that there might be more left over for this one, the right-hand estimate, than the midpoint. It looks like there seems to be less overage here. Then we're supposed to use it with 8 rectangles. I'm not going to talk through all this, but delta x now is 1/2. We do the same thing. We find the right endpoints at all those 8 intervals, sum them up, and then we're all supposed to do that again with the midpoint of each interval, and it gets pretty involved just with arithmetic. It's not any great advanced math, but you can see that estimate with the midpoint and 8 rectangles is getting pretty close to the actual area, which is 3.905, and that's rounded. And we're going to see methods for finding the actual exact area in the coming sections. So here is the that function x minus 2 times ln of x, and we can play with it and see with different rectangles and whether it's the right endpoint or midpoint approximation or even left endpoint approximation, what those rectangles look like. So now this brings us to the distance problem. So remember that when we were talking about derivatives, if we had a position or a distance function, we got its velocity. We could get the velocity from the distance or position function. But now suppose we have the opposite problem. Suppose we have a velocity, but we want to know the distance that something has gone in that time. So this should kind of be reminiscent of section 4.9 that we just did with the antiderivative. We're kind of doing the same type of thing. So think about when the velocity is constant. So if the velocity is constant, then you can figure out the distance you've gone very easily if you know the time. The distance is just velocity times time. So for example, here if I have my cars going a constant 45 miles per hour over 2 hours, I've gone 90 miles. So distance is velocity times time. And when you have a multiplication like this, you want to think of two quantities. You want to think in terms of the area of a rectangle. So if my velocity straight line is here, if you look at the area of this rectangle under the velocity graph, the area is equal to the distance that has been traveled. It's 45 times 2. So since we can find the distance traveled when we have a constant velocity like this, we should be able to estimate a distance traveled when we have a non-constant velocity by doing what we've just done, approximating with rectangles. So here's an example of a graph of a velocity function that's not constant. So it is showing it over a 6-second interval. So here it's at time 0, it's going 20 feet per second. At 1 second, it's going 7.358 feet per second, etc. So we can estimate that distance that this object has traveled with the rectangles. So what we're going to do, we have 7 data points, so we can form 6 subintervals. And if we form 6 subintervals, that's nice because delta x is just 1, since my interval is 0 to 6. And then if I do a left-hand estimate, notice that that's going to be an overestimate because this is a decreasing function. So my left-hand estimate, I'm using the left-hand endpoint of my first interval, which is 20, and the width is 1, plus the function evaluated at the left endpoint of the second interval, which is 7.358, the width is 1, etc. So I'm summing these function values each at this left endpoint, multiplying each one by 1, and I get approximately 31.56 feet. Now using the the right-hand endpoints gives me an underestimate. So this is called the lower sum estimate. So again, instead of using the left endpoint, I'm using the right endpoint of each interval. And again, delta x is 1, and I get 11.61 feet. So that's quite a difference. So I would need a lot more rectangles to get a decent estimate. And the actual value is 19.95 feet. So I would need to look at a lot more. So in summary, we've figured out a way to estimate areas under curved regions that sit above the x-axis over an interval of a continuous function. And we do that by finding n rectangles. So n may be given to us, or we might need to determine how many rectangles to use to get a decent estimate. We chop up that interval into n subintervals, form rectangles over each of those intervals, and then find the sum of the areas of each of those rectangles. And there's different methods to do that. So you can either find the height of the rectangle with the left endpoint on a subinterval, or a right endpoint, or a midpoint. So we looked at that, and we saw that these are the general forms for the right endpoint being used and the left endpoint being used, the sums of those areas, and that the area is the limit as n approaches infinity of these values. And we also saw that we can use this method to approximate the distance something has traveled when we're given a non-constant velocity function.